What a pleasure to be here and to have this opportunity. I owe it all to Professor Pradeep, who's been a prophet, a person with a vision, who's really seen what to do and with the goal ultimately of sustainability in the world. Very important for us to think about. Okay, we're going to, however, go on and start to talk about the interactions of water with hydrophobic media. And I want to talk about this. I now give you some facts and see if you agree with me. I claim these are facts. Bulk water is relatively inert, but an excellent solvent of polar molecules. We swim in it, we get rained upon a lot here during this conference. Okay, we drink it, life needs it. And water, we think very, very, very wonderful. Unless you drop sodium or something, potassium into it, water, pretty benign. Agreed? And so far? Okay, let's go to the second fact. Bulk water is neutral. What do I mean by that? As much plus as minus, as much cations as anions, all right? And it contains equal but very small amounts of H plus, we call that what? The hydronium ion, and OH minus, which we call the hydroxide anion, right? Okay. Water droplets are highly reactive, facilitating the formation of radicals and promoting redox chemistry. My first introduction actually to water droplets came when Professor Graham Cooks, come on in, and there's still a seat. Okay. Visited my lab on a sabbatical. And at that time, it was being used primarily as an analytical tool, looking for such things as drugs on money that people used. Okay, but you'll see it's grown much more than that. What else? Okay, let's try to go on. And water droplets are charged. Now, that's not appreciated by most people. That really, droplets are, I'll show you this, droplets are not neutral. You think of them, oh, water droplet neutral. No, they're all charged, okay? Larger ones are positively charged and smaller ones are negatively charged. I'll be saying a lot more about that, I think on a lecture on Monday. But we'll say something about this, but it's important to know this, okay? It's been recognized long ago to be the case. Okay, we go on. Please take a look at this because I think there's a lot of information in this. This is a plot of what? On the side, publications, aqueous, microdroplets, and reactivity. Let's see if this works. Right here, see? And this is against year. And what do we see? This is really taking off. This is a growing field. It's really emerging. What else do we see? Here is a publications by science area. We see that chemistry and physics are almost equally divided, interestingly, and other areas, okay, engineering. And what else? This is publication by country. The leading country for the moment is the United States. At the rate things are going, that's going to change, okay? And the second country will take over, and that's China coming up. What's disappointing, and I really think sad, is here's India. You can change this, and I really want to try to encourage you to think about doing this. And if I might stop a moment and explain why. You will, as you listen to this, you will notice that the equipment demands are actually rather small. It's very easy to set up these experiments. And these experiments, I claim, can change the way we do chemistry. You'll see this. Other people feel the same, okay? And there's huge things to find out. It's just the beginning, infancy, and many questions still don't have answers as to what's happening. Okay, so this is a very interesting plot, I thought. We go on. Suppose I go to a beginning person, what I call a freshman in chemistry at Stanford, And I say to that person, him or her, whatever, I say to that person, here is a beaker that contains 1 liter of water. The water's pure, if there is such a thing, but very clear. Okay, what does this beaker contain? And the student says, who's starting to study chemistry, oh, I think I know the answer. What? 55 moles of H2O. I'll remind you, this thing weighs, it's 1 liter, 1,000 grams, right? 1,000 milliliters, 1,000 grams, with me? And the H2O is 16 plus 1 plus 1 is 18. So 18 goes into 1,000, 55 moles. And a mole has Avogadro's number, something 6 times 10 to the 23. So it has a huge number of bent HOH molecules. And I smile and I said, that's right. And I said, what else does it contain? And the student looks at me a little puzzled and says, are you talking about isotopes? I say, no, I understand about isotopes. That's not what I'm talking about. What else does it contain? Pure water. He says, well, actually, we learned that it contains 10 to the minus 7 moles of H+. And because it's neutral, 10 to the minus 7 moles of OH-. And that's why we learned very early on in chemistry that the negative logarithm to the base 10 of the H+ concentration is called pH, and the pH of neutral water at room temperature, 1 atmosphere pressure, is 7. So smile. I say, now that you know this, I said, what do you think is the pH of a water droplet at its surface? And the person looks at you, and now you're a professor of chemistry, and you've asked this question. So the answer probably is not 7, but what is it? And no one's teaching this, so this is hard. Okay, we'll go on and think about that some more as we go on, but I wanted to get you the sense of the things are not as simple when we get now to interfaces as to what's happening. So you start to wonder about that a little. I hope you will. We'll go on. In bulk water, your H+ is solvated in 3 dimensions. Solvated, surrounded with hydrogen bonding with water molecules. And your OH- is fully solvated, right? And H+ and OH- do not make an electron transfer. Don't make .OH. We call that the hydroxide radical. And they don't make another radical, the hydrogen atom. Okay? And so the electron transfer process is endothermic in water. If it weren't that way, well, water would be bubbling hydrogen out all the time. I mean, hydrogens would find each other and make H2, right? And it's not so. We drink water, it's not that way. Okay. And if you make a calculation using DFT calculations, density functional theory, you'll find out that it is indeed endothermic, like 97.6 kcals per mole. I'm from the US, so kcals, multiply by 4, you'll get kilojoules approximately. So you're happy, okay? You know what I'm talking about. Fine. And you think, okay, this is nothing. What does this matter? Yes, it's true that if you have a negative OH- in the gas phase and you brought it to a proton, H+, the electron would jump. But what would happen at the interface? And now I'm using S to show you the surface of the interface. For liquid water at the air-water interface, guess what? The process is exothermic. And it's here's the calculation. It's really quite exothermic. It is really forming H dot and OH dot. They do, at least where I live, they don't teach this. At least not the beginning students at all. Yet it's so important to understand because it's going to be the basis of so much of what we're going to talk about, that this happens. A very important idea here. What more is going on? Okay, it's no longer solvated in 3 dimensions, but that isn't the end of the story. It is also true that their negative and positive ions will stick a different amount into the hydrophobic medium. As soon as you make a charge separation, you learn in physics, you have an electric field. And there turns out to be a huge electric field, huge compared to what you're able to generate in the laboratory. Not huge compared to what the electron in the hydrogen atom feels from its proton, okay, but huge. And we'll look at that in a moment, okay? And now, what I've told you, first of all, people initially don't believe. But here's work done by a postdoc in my group, Yu Xia, who's now become an assistant professor at Jianghan University in Wuhan, China, okay? He's returned. And he used a spin trap molecule. This one is called DUMPO. You could use tempo also. This one's DUMPO, doesn't matter. And this thing captures it, and you're able to see I'm showing you, you can see the red, which is the capture of the OH, and you can see in a nitrogen atmosphere, and you can see the green, which is the capture of the H. We really know it to be so. And then I'm showing you more things that you can pick up, things like O2 minus that happens at the surface. This is really important to see what's going on. All types of ion chemistry and radical chemistry is taking place. The way most chemistry is taught is you always write down balanced equations. You're trained to do that, and that they tend to be all neutral. This is false, okay? Because if you try to understand the mechanisms, you find out things stay balanced, but they aren't as simple as this. And they aren't all electrons being paired, all everything being neutral. Okay, and I'm showing you this. And I'm also showing you that the OHs, I'm going to show you more about this, the OHs find each other. And OH plus OH makes HOOH, that's called radical recombination. And HOOH is also called H2O2, and you recognize that as hydrogen peroxide. So that's where hydrogen peroxide comes from on droplets. And you really find even the rain that's happening to us has hydrogen peroxide. People thought, oh, it must be the action of sunlight high in the stratosphere. No, you don't need that. It's true in the dark too. Okay, we'll go on. And now, by how much does the interfacial electric field lower the energy to detach an electron from OH minus? And I think this is important because I'm going to be arguing to you that OH minus now gives up its electron. Oh, I can't get on the other side. Okay, have to go through the wall. Okay, let's look at that. No field, 25 degrees centigrade. Okay, OH dot to OH minus redox potential is like that, and depends on pH. So the detachment for 7 is about 2.3 electron volts. A lot of energy. Not as much energy as the ionized. Water, that's much more energy, but a lot, still it's 2 electron volts. Remember, electron volt is 23 kcals per mole, and multiplied by 4, and we're up to the kilojoules per mole. Okay, fine. Okay, the electric field dependence, okay, is E, capital ED. D is the effective displacement between the hydroxide salvation site and the electron's final location. Okay, that's going to be about 0.5 to 1 nanometer. A field that drives the electron toward its destination, that's the sign, lowers the energy. A field opposing raises it. When we work all this out and we understand what the Faraday constant is, we find out that for an electric field that you typically get at the air-water interface, okay, we find out that it turns out to be 1 nanomole separation. Nanometer, 1, okay. We get a shift of about 1 eV. So it becomes much more easy to pull off an electron now from OH minus. It doesn't always, okay, so you're getting to see that. So what is happening at the surface of a water droplet? H2O is in equilibrium with H plus and OH minus. Autoionization, we know what Kw is, right? 1 times 10⁻14. Okay, and at the microdroplet surface, the OH minus loses its electron to form the hydroxyl radical, and that goes on to can go on to recombine or to react. And it's captured by, for example, it's captured by OH, is captured by H3O plus to form what is called the water dimer cation, H2O plus. Now there's an argument in the literature about some people think it's really water dimer that's being ionized, whereas I think the lowest, in fact, the calculations show the lowest energy is really OH dotted into H3O plus. Okay, but let's not get involved in those arguments at the moment, but understand that's going to be there too. Very important species. How can we show this? People at Berkeley, UC California, Berkeley, and here's the group, actually synthesized this molecule. It has a carbon-boron bond. And if you have hydrogen peroxide present, it clips this bond and makes this thing, which some of you will recognize is called fluorescein. That's a fluorescent molecule. This is actually non-fluorescent. It has an IUPAC name. That's hopeless. Don't learn it. We're going to call it just PF1. Okay? Make it simple. And I'm showing you it does this in the presence of hydrogen peroxide. Now, let's look at this and see what happens. Here is water. Here's the bright field image of water. Here is its fluorescence when I'm shining light to excite the fluorescein. I see, I don't know what the rest of you see, I see nothing. Here is an air-water interface of a beaker. Here is the fluorescence. I see nothing. Okay? Now, look. Here is bright field with a droplet. And see these droplets? Here is the air-water interface, nothing there. But the droplets, they're lighting up. And you'll even see that the smaller droplets are brighter as we go on. Okay. I was so excited by this discovery with J.Q. Lee in my group, who's now at Seoul National University in Korea, that we sent this paper off to Nature about that we had discovered that water droplets make hydrogen peroxide. Magdalena Helmer was the editor, and she sent it out for review, which was good. Often you don't get things sent out for review. And the reviews came back mixed. Interestingly, they had a common word. One person said, "This is unbelievably exciting." Another person said, "This is unbelievable." Magdalena called me up, and people know me and use my name, Dick. She says, "Dick, people had been studying aerosols for years." She said, "If this was true, it would have been seen already. So we don't want this paper." Well, that's not a scientific argument. I gave up. So it got published elsewhere. I think in the Proceedings of the National Academy of Sciences. But okay, I'm trying to get you a sense of things are not easy when you do something which breaks the picture of what people accept. Been much better making a battery advance. That would have been accepted. Okay, now look, this is a fascinating thing that I'm showing you. Let's see if we can really see it. Here are 3 droplets. All of them have this PF1, 10 micromolar PF1 in them. And what do we see? If you're in the front row, you will see this one, which is A, 160 microns in diameter. Okay? It's just a faint green. You see it? You can see it, right? You in the back can't. Okay, I'm serious. Now here we go to B. This is 50 microns coming out. And here is C. C is 16 microns. It's bright. And look how this takes off. Okay? This is going to be the beginning of trying to understand things and why it's been missed. Big water droplets, miss it. Hardly. Big water droplets splash and form little water droplets, you find it. Okay? But it wasn't looked for. And it's there. It really is there. A number of you know this. But there are still arguments about this, and there are people who claim, oh, it's all due to ozone impurity in the air or something. No, it's not true. Okay, we'll go on with this. We want to try to understand this phenomenon, but here's the first hint that it's really going to depend on size. And I now want to show you work that was done at Columbia University with Professor Wei Min. This is, I sent J.Q. Lee. Here's a student who's gone back to Beijing who worked with him to do the work. These two really did the work. And they observed a stark shift in a molecule. Stark shift, when you apply electric field, you change the positions. And how big was the stark shift? It was about 5 wave numbers. And when you work it out, it turned out to be an electric field of the order of, in this case, 10 to the 7 volts per centimeter, or 10 to the 9th volts per meter. That's what I'm telling you about, a big field. This is true generally of all types of membranes. If you take courses in biology, you're always learning about there's an electric field at the membrane. Well, there is here too. This is a membrane in the same way. And it's there, okay? It just are not talked about as much. I could go on as to how this experiment's done, but you get the sense of it, okay? Now I want to go on to some very recent work. This is going to be early evidence that curvature of the droplet is important. This is work done in my lab by Kyungmin Lee. And he's now back in Korea, okay? And also I had a visitor who had a green card, Masoud Mirgardi, who comes from Iran. Since I worked with him, Stanford University has investigated me for my ties to Iran. I'm not Iranian, and I've never been to Iran, but I'm trying to give you the type of climate I live in. Okay? This is real, what I'm saying to you. And Stanford has good reason, because it could lose huge amounts of money with charges about what I've done, how bad I was. Okay, okay. So here it is, and this is a figure from a recent publication, I think in JACS it was, Journal of American Chemical Society, and we're looking at this droplet, and we're using this particular thing called Amplex Red, which with H2O2 forms this thing called resorphin, which then shows up easily. Okay, and it shows up red, and you can see as we change size how this increases. So it's very, very clear. And I want to, okay, so this is the schematic illustration of the experimental setup that's shown here. Very, very simple setup. This is why I'm telling you it's so easy to do these experiments, to set them up. Okay, here we have a detector, okay, a light source for making fluorescence, okay, and we just spray. Is it simple? Okay. And I'm showing you more of this work. Let's take a look at it. This is the time-lapse fluorescence imaging and reaction kinetic analysis of the generation of hydrogen peroxide in water microdroplets. Now, A is the fluorescence images of microdroplets with radii of what? This one's 40, this is 15, this is 8. These are microns. I'll remind you, a human hair is about 30 microns in diameter. It varies with the person, but it's on that order. So that's what we're talking about. They're small, okay? And we can see what happens. B is the H2O2 concentration generated by microdroplets through the radii of this. And C is the rate of production per unit volume, okay? That's this, okay? The reaction kinetics were assessed by analyzing the slope of the H2O2 production during the initial phase until approximately 200 minutes. And it grows. It doesn't turn off. Some people think, oh, it's there and it stops. Well, it actually can go on and do this and so forth. And then what else do we see? This is a plot of 1 over R of the H2O2 production rate. And interestingly, it's showing nearly linear dependence upon 1 over the radius. That's the first hint of curvature of what's happening. We'll have more to say about this. Okay. So now I'm going to show you another experiment. This one primarily done in China by Yu Xia, with knowing what happened in our lab and following this up collaboration. Here he has a piezoelectric device and can launch single droplets into a mass spectrometer. You've heard enough about mass spectrometry. I'm not going to explain it to you, right? So you feel you understand what's going on. And the force from the piezoelectric device controls the size of the droplet, and the frequency of the driving signal controls the frequency of the droplet. And you can change the opening size and control the droplet size, and we're going to see it. I hope the next is a video. Now I need to play the video. So let's see if I can make the video play. Okay, good. Let's go. Let's watch. Here's 20 microns, and they're entrance into the mass spectrometer, okay? And here goes 60 microns. It's bigger. You can see it. We're going to look at individual droplets. So we are not talking about droplets interacting with other droplets at all. We have individual droplets that are going to be studied. That's a bigger one. That's the 140. Okay, so you know how this is now done. And this is sort of like an inkjet printer. This is a droplet on demand mass spectrometry, if you want. Again, not difficult to set up if you want to do it, but not commercial either. Okay, so now here are the people who did the work. This paper has just recently been accepted for publication in I think it's PNAS again. Okay, and I've been very fortunate to work with other collaborators like Bolei Chen and Xinxin Chang. Okay, and this is the wife of Yu Xia. Okay, the mass peak at M over Z36 is called the water dimer cation. Its structure is thought to be OH combined with H3O plus, which has the lower energy than this. We use its intensity, which we're going to note as I36, as a measure of how reactive is the water droplet. We want to look at that's charged, right? So we can see it with the mass spectrometer, and we're going to follow its intensity to learn about how much is produced. So far, straightforward. Okay. Here's what it looks like if it's just a function of surface area. Because people first thought, oh, it's just surface area, you know, and no, if it were just surface area, it would go like this. It's doing like that. It's not surface area, okay? This is instead 1 over the droplet radius. This is the I of 36 per unit area, and it's going almost linearly with 1 over the radius, and it's really due to curvature. So the I36 signal does not vary linearly with the surface area of the droplet. The I36 signal normalized by the surface area of the droplet varies nearly linearly with the reciprocal of the droplet radius. That's what is shown. Now, I'm going to bother you next with a simple model explaining how curvature arises and how it affects the electric field at the surface, because it's actually curvature which is determining the electric field, I'm going to argue to you. Okay? So look, it's very hard. I don't know. Thomas has more experience than me. Very hard when you present math in a lecture. What do? First of all, I forgot to tell you, anybody who wants a copy of this lecture, just email me at my email address, my last name, Zare at stanford.edu, you get a copy. So just relax, and you don't have to understand every step, but you'll, okay? I do want to show you, though, how it's done. And I also want you to appreciate why it is that some people spend their time really worrying about this type of stuff. And so it's going to be a combination of things. So let's begin. We're going to look at the electric field at the surface of a charged spherical droplet containing a 1-to-1 electrolyte, like like Na plus, Cl minus, or anything like that, okay, or H plus and OH minus, 1 to 1. So we're going to begin by considering a sphere of uniformly distributed dipoles having an infinite radius. What does that mean? Uniformly distributed dipoles plus and minus separated, right? That's a dipole. They're going to be all aligned in the same direction, and I want them infinitely in expanse. That's a sphere with an infinite radius, right? Okay, that's like a capacitor plate. Some of you may know already there's no electric field inside, above and below a capacitor plate. There's an electric field inside, but not above and below. And I want to make this very clear, and I know it's going to bore some of you, but others for you, this will show you why you wanted to know this stuff, okay? So we're going to start. We start by considering an infinite plane of positive charges with surface charge density, okay, sigma, and in coulombs per square meter. We want the electric field produced by this plane. So we just take those that are all plus. This is just half the capacitor plate, right? Because the plane is infinite and uniformly charged everywhere, right? The field must point perpendicular to the plane, no sideways direction, and the field must have the same magnitude on both sides, up and down. Okay? Now we're going to use what we call a pillbox, a short cylinder of top and bottom surface that straddles the plane, goes back and forth. And we're going to apply something called Gauss's law about the charge that's enclosed by this thing, right? And the total electric flux through the pillbox equals the total charge enclosed by the pillbox, namely sigma, that's per unit area, times the area, A. So that's sigma A, and then divided by the permittivity. And when we do this, the A that we get, okay, cancels out because it's sigma A, and there's an A times this, okay? So it's just sigma over 2 epsilon naught, okay? And that's the magnitude of the electric field is constant above and below the plane of all charges. Fine. Now, we take pluses above and minuses below. Consider 2 infinite parallel sheets with equal and opposite uniform surface charge densities, plus sigma and minus sigma, separated by an even infinitesimal distance d. Okay, field of one sheet, a single produces a uniform field of this magnitude, pointing away from the sheet. The other one points towards the sheet. You add the two together, and they cancel. No electric field. No electric field above or below. Electric field inside. Okay, and fine. And everybody says, okay, you know, I know this, so what? So far, right? Now, we got that. Let's go on. Let's consider a solution that forms a spherical droplet. Why is it spherical? Surface tension, right? Wants to minimize the area for the volume. So we can make it spherical. There are 2 kinds. Ooh, come back. There we go. There are 2 kinds of ions. Positive ions, that's plus Ze, and negative ions, minus Ze. We're going to be neutral, remember? And we assume the solution is overall neutral. And so there's the same amount of positive as there are negative. And the bulk concentration of both is, we're going to call that C naught, how much we put in, how much we've added. So far, okay, I think. Now, in a region with electrostatic potential psi of R, the ion concentrations change. And from statistical mechanics, the total concentrations follow a Boltzmann distribution. Okay, so what's a Boltzmann distribution? It looks like this. It looks like minus the charge, that's minus Ze. This is for this, okay, psi R, okay, and this is KB. What's that? Boltzmann constant. And what's T? The absolute temperature. And so that's the positive ions are repelled, and this is what this one looks like. Fine. And so finally, let's put them together. This is going to be the net charge density is then given by the sum of these two. Okay? And that's this plus this. And then some of you will hazily recall That is the hyperbolic sign, okay? and so that should be what rho of r is. It's like that. And he said, oh, this is getting awful. Where is this going? Let me go on. This can be written as a power series. And for small x, which is what we're going to have, this thing just keep the leading term. And so this thing looks like this, really. Not quite, but it looks close to this. And this thing that I've just written down is what's called the Debye-Huckel approximation. And this was published in 1923. So everything I showed you is not original at all. It's just really all taken from what Debye-Huckel did. And people who worry about double layers and all this is to them understood. Okay, but for those of you who haven't spent much time with this is new. And that's where it all comes from. Okay, we got it. It's this. Fine. Let's work with it. I'm going to define something called the Debye length. And it's often written as lambda d or 1 over kappa. And it is a fundamental quantity in electrostatics and electrolyte theory. And it describes how quickly electrostatic interactions are screened in an ionic solution. And mathematically, for a symmetric monovalent electrolyte, it really looks like this, okay? In which that is the electric permittivity. And the dielectric constant of bulk water is about 78, but at the interface, it's thought to fall down to 4. This will not be important, but for us, it's real, but I wanted to show you it's not the same. We'll go on. The radial distribution of electrostatic potential is governed by the Poisson equation. Okay, this should bring back memories of beginning electrostatics, I hope. Those of you who've done that, okay? So great, it's this, right? And so now let's substitute for rho of r. Remember what rho of r was? We can go back. When you plug it in, it's just kappa squared. It's this differential equation. You can solve it, and better than trying to solve it yourself, you can plug in the solution, which I'm giving you, and you can see that it satisfies this. Now, if we had more time and we have a blackboard, we would go through this. You can convince yourself that's a solution. That's what psi of r looks like. That's, remember, the electrostatic potential. It really looks like this, where A is an undetermined constant. Now, at the very surface, I'm going to call it capital R, at the end of the radius, capital R. Okay, this thing looks like this, okay? And this is a negative gradient, the electric potential. The electric field is the negative gradient. So let's take the negative gradient now. We work it out. Here's the answer, okay? So at a droplet surface, okay, this is what E of R looks like. It looks like kappa psi r times this. That's a constant, basically. And this thing is 1 over kappa r. The kappas cancel, and that's a 1 over r term. That you have a constant plus have a curvature term. That's where it comes from. Okay. Now, look, it doesn't matter whether you follow this math or not. You have some feeling for that it has a basis to it. And then under our experimental conditions, ultra pure water with ionic strengths of this arising from autoionization and dissolved CO2, the Debye length is given a value about this amount. And for droplet sizes examined here, we go through this. For small droplets, the curvature effect and the magnitude electric field closely is 1 over r. So the area of a spherical droplet scales as 4 pi r squared. That's the area. Okay. The effective curvature of the spherical droplet is less than 20 microns on the electric field. The effective curvature of the spherical droplet of less than 20 microns scales as 1 over r. And the curvature of the droplet enhances the electric field. So we're seeing the electric field going up. Now, I want you to remember, why is that important? Because the electric field goes up means we take OH minus into OH. And we get more chemistry. Okay? Real connection here, physics and chemistry going on through this process. Okay? And so here it is. The curvature of the droplet enhances the electric field of the surface of the water droplet, which drives the production of hydroxyl radicals. So you might say, great, wonderful, But is this the end of the story? And now I think I may have a bit of a surprise for you to think about as we go on. No, it's not. Okay, no, because more OH dot gets generated, and you have actually two competing processes going on. You have OH reacting with your solute, whatever it is, and that'll be linear in the OH radical concentration, and you have OH recombining with itself to form hydrogen peroxide, and that will be quadratic in the OH. And if you keep upping the OH, at some point, quadratics beat linears every time, okay? And so this means that there should be an optimum size for getting a yield in a droplet. Okay, that's not been said before, to my knowledge. And okay, now that I've said it, let's prove it. So here's the experiment I want to show you. This is something called melatonin, and it's used to scavenge OH hydroxyl radicals. This is melatonin right here, okay? And it goes ahead and it forms things like, see, H plus goes on and you can pick up the ions, so we can use a mass spectrometer to look at this and other stuff, and this happens like that and so on. We're gonna look at all this. Now we wanna see what happens. We can see all the melatonin, what its form is, and we can compare it to the production of this. Let's look at what happens. We're gonna call that, I don't know if I bothered to show you, that's a 250. Sorry, let me do this again. That's a 250, right? I'm gonna use I of 250, that's shown right here. And I'm gonna plot this versus droplet surface area. You're gonna remember, I can control the droplet size, and I showed you how with this droplet on demand mass spectrometer. And look, once again, it's curved. What if I plot it against 1 over the droplet radius? I'm now looking at the production of I-250, nearly linear, not quite, but nearly linear. What I was telling you, it really depends on curvature. And now, what about if I look at the product? The product is summing all the things, it's the fraction of melatonin that's being converted into the products. And look, it looks like this. I see a peak, okay? It goes down. Okay, well, okay, that's maybe true of melatonin, but is this true of other things? And so here now is methylviologen. That's this molecule. Okay, methylviologen, better known as paraquat, is a well-studied redox active molecule that acts as an electron mediator in electrochemistry, photochemistry, and biological systems. Okay, MV plus 2 is the dication bipyridinium species. I'm not going to say all that. You don't need it. But I have to put it up. People have to, okay, look learned. Because of the strong positive charge, it's highly soluble in water and undergoes well-defined stepwise 1 electron reductions. It forms both MV plus and MV plus plus. Okay, that's methyl violet. MV is methyl violet. So we now have accepts 1 electron to form the methyl violet radical cation and so on. Here's the mass spectrum showing reduction product of methylviologen in single aqueous microdroplets. And okay, the total product signal is calculated as the summed intensities of 171 and 185. I'm showing you what they are, and 186. Okay, so we know what the product signal is, and we know everything. We know the starting material. It's going to be important for you to understand how this experiment's done. Okay, and now, and this has been studied before by these people. Not the data, but this type of mass spectrum that it's known. Okay, I'm showing you this. Now it should become familiar to you. This doesn't work. Okay, this is the intensities of the products of methylviologen measured from the droplets of different surface areas. Error bars represent 1 standard deviation based probably on 3 measurements. The dashed red line represents the expected behavior if droplet reactivity scaled with droplet surface area. Got it, right? Doesn't work. Here's 1 over R. And, okay, and the data are normalized by the surface area of the droplet and plotted against the reciprocal of the radius of the droplet. Error bars represent, again, 1 standard deviation. Look. Okay, and now let's look at the fraction that makes the product. Let's look down. It peaks around here. That's about 0.15. That's 1 over the droplet radius. So the droplet radius is about, what, 7? Okay, it's about 7 microns is the best for making the most yield of product. This is interesting. And I'm showing you again how it's calculated. Now, I thought this is news, at least it was for me, okay? And it gives real insight into what's in part driving some of this chemistry and why it is just smaller is bigger, is better in a lot of this work with interfaces. So if you want to, for example, cut a mineral, which is what you've been doing, you want actually small droplets will be better than larger things, okay? So the rain splash is more important than the rain, etc. We'll go on. Now I'm going to talk about an application, and I'm going to talk about making bleach. Bleach is important. Just ask my daughter in the audience who does nursing, etc. And it's used all the time for disinfection. Okay, so bleach, common material, right? This is work done with Professor Wei Di, okay? And he's head of the Iontronic Laboratory in Beijing, and has been a visitor to our laboratory, okay? And this is, I'm showing you work unpublished, just submitted, so please understand what we're doing. But you know, you want the latest word, here I am. And I want you to see what's going on. Okay. The modern approach to making bleach starts with the electrolysis of a saltwater solution. Okay. The reaction produces 2 key products, chlorine gas and sodium hydroxide, caustic soda. Right? Put in salt water, put a current, voltage. You agree? This is so. The chlorine gas and sodium hydroxide solutions are separately collected, anode, cathode type stuff. And then the gases bubble through the liquid. And what do? You get sodium hypochlorite, the active bleaching compound, which is then sold as a liquid bleach. And there's a whole industry, billion-dollar industry, something like that, based on making bleach this way. Okay, and that's fine. Now I'm going to show you a very different way to make bleach, but one that I think will now resonate with you when you think about interfacial chemistry. Okay, our approach adds fluorinated ethylene propylene powder. I'm telling you, any particulates are helpful, and particularly hydrophobic ones. And this is basically ground up Teflon. It's like it, okay? And this is why the whole area of atmospheric chemistry gets changed by understanding that water is always forming on little pieces of dirt in the, particulate matter in the atmosphere, and that all types of chemistry is taking place. Okay, and then at the interface, okay, we get OH dot plus Cl minus, okay, makes OHCl minus. Where's the Cl minus coming from? Na plus Cl minus from salt, okay? And then this thing goes on with H3O plus. You recognize that? That's the hydronium ion. That makes dot chlorine, okay? Dot chlorines are going to find each other, okay? And you might worry that they're going to make things, but dot chlorine will find dot OH and do this. You get actually HOCl. And because they're so close to each other, we don't actually get chlorine gas evolving. We really get just the hypochlorite. Okay. And so I want to, again, show you the difference. Here's the chemical plant. This is now how it's done. Okay. Ocean water in either case. Here we go. And here is our particles, and we're done. Seriously, we're done. We just have to sprinkle in the dust and have a filter that takes it out, and we got bleach. And I'm hopeful that this can now be scaled up and made into something that's important. Hasn't all been done yet, once again, but this is the start of something new. I want to go on one last topic. I never gave this lecture before, so I'm going to clearly run too short. I'm sorry about that.
No, we have time for questions.
Okay, so how the size of the hydration shell varies with the nature of the alkali atom. I don't know if you've ever played much with this. People say, use salt. Well, it turns out there's all types of salts, right? Not only is there sodium chloride, there's many other salts. Does it vary with the salt? And the answer is yes. And I'm going to show you and try to explain to you why. And this is, I think, again, be interesting. Please notice, if you will, the interplay, I think, between physics and chemistry that's going on. And all ultimately headed towards biological purposes. It's very interesting. Okay, so let's look at it. Lithium plus, first hydration shell. Here's its distance, strongest hydration, largest effective hydrated radius. Okay, here's Na plus. Okay, now it's got this intermediate hydration. Here's K plus, weakest. And I'm going to show you that potassium chloride is much more effective than sodium chloride. And lithium chloride's worse. And rubidium chloride would be even better, but then it starts to cost money. Okay, we're going to look at this. The outer Helmholtz plane, OHP, is the boundary in the electric double layer between the compact immobile stern layer at the charged surface and the start of the diffuse layer. It is defined as the plane passing through the center of hydrated ions that approach the surface without specifically adsorbing. They keep their hydrated shell. Inside the OHP are specially adsorbed ions, okay, and the rest of the compact stern layer. Beyond the OHP, the ion distribution decays into a diffuse layer. But you really have what's called a stern layer right at the interface. The electric potential drops sharply from the surface potential to the stern potential at the OHP. Further decay in potential occurs through the diffuse layer. Okay, there's electric field, but it's falling off. The position of the OHP depends on the hydration size. The smaller the hydration radii, let ions get closer, nearer the surface, higher counterion concentration and stronger interfacial field. Larger hydration radii keep the ions farther apart, the OHP farther, lower concentration and weaker field. And here's the data that's been obtained. I'm going to just try to read it. This is the production yield I'm trying to read it. It's micromoles per gram per hour, I think it is. And this is Cl minus concentrations. We took 3, 0.2, 0.5, and 0.8. But you see what they are. And what are we talking about? The best is KCl. Okay? The worst is LiCl. And this is what they're like. So there is a real variation. Now, why stop with one chlorine when you can go on and you can form others? Even better is barium dichloride. These compounds may not be known to you. They're known to Professor Nanamani very well, as I'll show you in a moment. But there's big differences in them. What about we put these in and see how they influence it? And I need to define what is TMA, TEA, and TPA. So I need to tell you what they are. and that's shown here, okay? I am not an organic chemist. He is. And, okay, so these are very familiar. So we really see them. That's tetramethyl, okay? And we can see how they vary in size. See how TPA is and so forth? It really pushes out. I'll keep waters out. Okay, now let's go back. I can go back. Okay, see what this is? Like so. And CTMA goes much better. Okay, what's happening? Okay, and so we now come to this. Cations with smaller hydration radii demonstrate reduced Stern layer thickness, elevated ion concentrations, and enhanced triboelectric field intensity. And that's indeed what we're finding when you go through this all. And we're getting this type of electric field effect, how it's varying again. Not this makes it look large, but it's 1.2 to 1.5. It isn't that large, but you get some idea of what's happening here. So we now are beginning to get an understanding of adding different solutes to our system and how they affect the chemistry. And I think that's probably the last of what I had to present. The conclusion, okay? Reduced cation hydration sizes enhance both the interfacial triboelectric field strength governing the reactive oxygen species kinetics and the local anion concentration in the reaction zone, resulting in higher active chlorine yields. And so we could actually control some of this and have an understanding why, what's happening. I'm going to stop here with slides, and we can have the lights for a moment. I do want to thank you. I do want to tell you where all this is, I think, going. There's going to be, in my opinion, a revolution in how we do chemistry. It will be very much promoted, I hope, by interfacial effects that involve things that can form radicals and ions. I think water plays an important role. Many people first say, keep water out of organic chemistry. No, I'm telling you just the reverse. You actually want to use it. And starting with the on-water reactions that Ron Breslow and Barry Sharpless made very clear, much is going to happen this way. There's room here for all types of people here in this room to contribute. This is a new field, new possibilities. It is also a green chemistry because it's water, because it's being done at room temperature. Because notice, I'm not applying an electric field generally. I can, and I can gain some by doing that. I'm not saying you shouldn't. I'm trying to show you, though, it already has an electric field from the interface that's built into it. And so I urge you to get involved in this. I stop there.
Sir, a very exciting lecture talking about the curvature, how it creates interfacial electric field, and this new interesting study about making of bleach that says you can prepare HOCl, that is hypochlorous acid,
Yes.
at the interface.
Right.
So can't we think of making different hypohalous acids in the same way? And what is the production yield in this? Is there some different products are also forming along with it?
I have an amount made per hour for various amounts you put in. I don't have it in my head, but I can share with you what's going on. It looks to me like it could be brought, hopefully be made even commercially this way. It could really change the way you make bleach, I think. I'm hoping. Okay. And
Can this microdroplet chemistry be a replacement for hydrothermal reaction? Use the microphone.
Let's understand. Can microdroplet chemistry be a replacement of what?
Solvothermal reactions.
For
solvothermal reactions.
why not? Sure.
So it can be very fast process, like for making nanoparticles.
I mean, the speed, you get great gains in the rate and the speed. and also the cleanliness, the eco-friendliness of the system. So I'm very hopeful about this.
This is in a way what we have done, what Anamani was talking about, this micro droplet. This process is hydrothermal. Almost,
You're right.
you might think like that.
Right now, again, let me stop a moment and again say to you that it really is all happening at the interface. I hope I convinced you of this, and that I want to also stress to you what I've told you about in terms of droplets also apply to bubbles. Okay?
Hello, sir. If we
Maybe
change,
briefly introduce yourself. It might be helpful for
I'm
the camera.
Chris, I'm from IIT.
Yeah.
I'm pursuing PhD there in third year. So if we change the pH of the solutions, if we change the pH of microdroplet, so it will facilitate the reactions, because I did a zeta potential study that you have explained, like stun layer. So if we increase the pH, like if we make the solution more acidic, it became more positively charged. If we decrease the pH,
Okay, if you increase pH, it becomes more basic. But I mean,
sorry,
if you decrease the pH, it becomes more acidic. Okay.
Yeah, if we decrease the pH, like we make acidic pH, give more positively charged.
Yeah.
And if we are adding more basic solutions, give more negatively charged. So the charge distribution can facilitate these reactions.
So it does. You can vary things by changing by changing the pH. That's there too. You can also apply external voltages to change things. All is possible. And then I want to point out to you again that, and I will on Monday, I think it's Monday, that droplets, small and large, will have different charges themselves and will act differently. Yeah.
Hello, sir. Very exciting lecture. Everything you talked about.
Introduce.
Sir, my name is Sinchal Mukherjee. I am from Professor Pradeep's lab. I work in this field. So everything we talked about this macrodroplet chemistry about OH minus OH radical. So is there any study about this methoxide radicals OCH3 minus? So do they behave like the same, or they can enhance the reactions, or they can behave differently? CH3 minus, OH minus, or methoxide?
Where does CH3 minus come from? Pardon me.
Methanol, from methanol.
Well, methanol doesn't hardly make much.
Okay,
I mean, we've tried that. A little bit of water in methanol works because of the water, but if you make absolute methanol, it doesn't ionize that much. I hope really. In fact, we just shut reactions down when we try acetonitrile and methanol. Now, I've always been interested in what will happen with ionic fluids, and I have never had anybody else. I've never gotten anybody excited yet to try that, but I really would like to see that tried.
thank you.
Okay, but we see this water, which we think we know so much about, it still has mysteries for us that we're learning in special properties. Yeah.
So myself, Palak, I'm from IIT Kolkata.
Okay. Thank you for coming assistance. Sure. Yeah.
So, sir, there is some sort of electric field generating at the interface. It has some sort of magnitude, right?
It does, and we measured it.
Yeah. So, can that field be used for sort of like a kind of electrolytic cleavages, right? Without applying external electric field?
It can't be used for the little micro droplet becomes a reactor. That's what's going on, and you're getting electrochemistry. You really are, without applying. Now it can help you by applying a voltage, but you don't have to apply a voltage to make things happen. Okay.
Thank you.
Thank you, Professor, for a very interesting talk. I'm Deepak from IIT Madras, working with Professor Pradeep. I work in completely different, but I have some curiosity when you're talking about the droplet size increase, so it should become the positive charge, and when it decreases, it becomes the negative charge. So do you have any idea at which threshold we change the polarity? And this can be used as an employee in the organic chemist point of view, like where they can tune the polarity in the organic system with this. Do you have any comments on that?
I'm not sure I know how to comment on that. You have any comments you want to make?
if it is forming waves and negative charge, they actually can do the basic reactions. But it's, of course, it depends on the particle size. That's why actually when we vary this distance, of course we see the difference in the reactions. So do you have any comments about the when the threshold, like when it's changing the polarity? So going from smaller droplet up.
What happens, the electrons that come off of OH, they move and they go to the smaller droplet. Why? Because the smaller droplet has a bigger electric field. We just went through that.
Anyway, they can levitate in the electric medium.
They can be.
What is the size of the droplet which will levitate?
Oh, I showed you the electric. Generally, smaller is better to a limit. When you get too small, a water molecule itself won't work, and even a small cluster doesn't work. You need, I don't want the electric double layers overlapping. I want them to be pulled apart.
So I just wanted to add that long ago, Faraday did this experiment. That how did he show that oxygen is paramagnetic? Well, a bubble with oxygen in it
Yes.
went in that direction when the magnetic field is applied. Whereas nitrogen went in the other direction. Okay? I'm just asking you, well, if you're so excited about this one Faraday inspired experiment, should the droplet apply an electric field? Okay?
I'll show.
At that particular characteristic size, it will not bend in either direction. Otherwise, it will go in either direction.
And I will show you the actual experiment being done on Monday in the chemistry department lecture on just that, on applying positive and negative plates, having droplets go between them, and you'll see what happens. It is actually something called the Lenard effect. Okay, you come across that? And this is the physicist Philippe Lenard, who got the Nobel Prize in Physics in 1905. And it was an avid Nazi. Say more about that.
This is Uttam from IIT Guwahati.
I've been there.
Learned so many things. So, more specific to this, like when you say like interface, is it like the air-water interface?
Yeah, but let me mention to you, not only is it air-water, it's air-oil. Water oil. It's water silica, water particles. You notice water on ground up Teflon.
Right. So,
right? I'm all of those interface.
So it doesn't really matter like whether it's
it matters in the sense that the effect gets larger or smaller, but it doesn't. But they all happen. Yes.
Okay. So another thing is like how you basically comment on the rate of evaporation of the water and how that.
I've looked into that because early on it was believed that water evaporation was what was driving this process, but water evaporation takes time. And it's not fast enough compared to the time of flying into the mass spectrometer. So what we've done.
If you maintain this reaction in different humid environment, relative humid environment,
you can play those games, and there's much more interaction of gases hitting the water droplets as to what happens. And I was trying to show you O2 forms O2 minus. Okay, that type of thing.
I have a question. You assume that charge on the drop is uniform. The water is an insulator. Is it uniform or it's patch?
It's patched, but it's uniformly patched. Right? There's no. It's like random. How to say? It's taken as uniform.
So electric field cannot be totally uniform.
No, not totally, but very close. I mean, very small. No, not. But a larger, yes. Looks uniform.
So we're going to use the Gauss's law.
Yeah, I think so. Yeah.
Yeah, very interesting aspects that you have showed, because I'm Gopukuma from IIT Kanpur.
Mm-hmm.
I am from condensed matter physics, so I was not very familiar about this aspect. You showed that when you make tiny droplets, you will suddenly find peroxide in it. So my curiosity is like, you need to definitely have these droplets running around to do a chemical reaction to have reactivity. So the chemists who do the bulk synthesis of bulk reactivity. So they use a bulk water rather. So how would you propose that this could be used in a way that we can have more?
Stop using bulk water and
No,
spray it
I mean,
into
it is
droplets.
a
I mean, it's very simple.
That's what I was thinking. You know, how do actually chemists would sprinkle water during their chemistry? Would you?
Well, people started to do that by, believe it or not, shaking it. They found that that they make an organic phase next to a water phase. They separated. They're not soluble in each other. But you shake and you get things to happen. And I think it's the droplets. And we've seen this recently. Another publication that just may amuse you. I hope it will amuse you. People are finding gold nuggets in oil reservoirs, oil wells. Where does the gold come from? It's weird, right? Well, it turns out gold salts are soluble, and water droplets that contain the gold salts at the interface with oil, you get redox chemistry. I hope I've shown you that. And your gold gets back to gold zero, U0, and then they accumulate and you get gold nuggets. Really, and the same thing with silver, how you're able to get, so I think Professor Nanamoni spoke about that too. And you can make alloys.
One more question. The size of the droplet, the critical size, which you showed about 7 micrometer. So what exactly is happening when you even reduces it further? I couldn't grasp.
Sorry, maybe not make it clear. It's still working, but it's turning out it's producing so much OH that the OH is finding itself first and is being depleted compared to reacting with a solute.
Thank you so much.
Okay.
I have one comment. Fantastic talk as usual, and it opened up a lot of questions. I was just curious that at this very small sizes, what could be happening to biology?
Oh, I have a whole talk about that. No. So please, I want to tell you something again, not being appreciated. In our cells, we have things called coacervates. We have biomolecular condensates. And we're finding that people have not recognized that all types of chemistry is happening on these little particles inside cells. And we're seeing things in the citric acid cycle, the Krebs cycle, that are being promoted by this. So it has great biological significance. Okay.
I mean, you commented on that also in your talk. So in the evolution of molecules, I was wondering whether the early molecules, there must have been some significance to the polymerization, nucleic acid formation.
Yeah.
What are your thoughts on that? Have you looked at any?
Yes, we have. And this will fit it much more into Monday's talk. And no, I'm not trying to put you off. I'm trying to explain, or maybe to get some of you to attend. We find that, I didn't mention, that oppositely charged droplets close together, or when they fission off, you get micro lightning. You get an electrical discharge. And that electrical discharge, we've been able to repeat all the same experiments that Miller and Urey did to build up the building blocks of life, using just water sprays. And water sprays are common, ocean on rocks. So there's lots. And then you go through wet dry cycles, which can lead to polymerization because the stuff collects in crevices. The idea of lightning in the sky making something is, I'm afraid, absurd. And that, I'm sorry to say, because the air is huge. You have to accumulate it to make something happen.
I suppose you can do a lot of science in Delhi.
Yes, but truly, and I've tried to tell people in Delhi this too. These particulate matters go into your brain. Yes. I'm serious about that. People think, oh, it's affecting your lungs. I'm telling you, it goes through your nose into your brain, and it causes all types of problems in your brain. Thank you.